Hello everyone, welcome back to the course on measurement and instrumentation, and today is the third lecture of our 10th week where we are discussing about signal conditioning system. Today we are going to discuss analog to digital converters or ADCs. We have already seen DAC or digital to analog conversion in more detail. So analog to digital conversion is required because mostly we have to deal with analog signal. So you talk about any real world signal from any of the transducer, maybe it's a temperature transducer, maybe it's a pressure transducer, or say if you are trying to measure light or sound, whatever you try to measure, the signals that you get mostly are in the analog form. Okay. Now an interface is required to convert analog signals to digital form. Analog to digital conversion is slightly more complex than digital to analog conversions that we have seen previously. A number of methods may be used for this purpose. Okay. The conversion of analog signal to digital signal occur in three different stages. The first stage is sampling of the analog signal. Okay. So let me consider a analog signal. Okay. I want to convert this into a say digital signal or a discrete signal, maybe something like this. Okay. Of course, this is a phase modulated signal, maybe I may like to have just amplitude modulation for example. Okay. So I want to discretize it. Okay. So the first stage is in this process is sampling. Okay. The second stage is the quantization and third stage is the encoding. This is the final stage where at the end you will have the binary output. Okay. So sampling is the process which converts a continuous time signal into discrete time samples, and this has to be done following a sampling theorem. Okay. And sampling theorem says that the sampling frequency Fs should be greater than or at least equal to twice of the maximum signal frequency, or we call it say F max. So Fs, which is the sampling frequency, is at least equal to twice of the maximum signal frequency, or it should be larger than that. Okay. And this particular criteria of Fs larger than or equal to 2F max is known as the Nyquist criteria or Nyquist. So there are different issues when you have Fs less than 2F max, okay, or the sampling frequency is less than the twice of maximum signal frequency. Okay. When you have this kind of situation, when Fs is less than 2F max, aliasing occurs. Okay. And aliasing causes distortion of the reconstructed signal, which is reconstructed from the digitized signal. Okay. So this analog to digital converters or ADC require a very important circuit that is known as sample and hold circuit. Sometime you may find it written as S/H circuit. Okay. We call it sample and hold circuit. We will also learn about sample and hold circuit when we will discuss our last module, or at least second last module, but sample and hold circuit, let me just introduce you to this particular important circuit when you talk about analog to digital conversion. Okay. Now let us consider again pressure transducer for example. Okay. And I am having analog input, okay, and I want to digitize it. I want to have a say digital signal, maybe in the form of something, say let us call it 01101, something we want at the output. Okay. Now let me call it, say this is the pressure transducer. Okay. It is generating this analog signal and this is my ADC. Fine. Now this ADC requires a constant input during the conversion stage. Okay. And this is exactly why you need a sample and hold circuit. Its function is to sample the analog signal and to hold the value constant during the conversion. If you do not hold it for certain amount of time, maybe fraction of second or fraction of millisecond or in say microsecond, there are different problems. Okay. So as I have just mentioned that real world signals vary continuously in time, or they are analog signals. Now if the ADC starts converting while the signal is changing in the input, okay, what will happen that the digital value will be inaccurate and therefore signal must be frozen temporarily. Okay. Now consider the same example. I have pressure sensor or pressure transducer. It is giving the analog signal and then I have ADC. Okay. Now ADC is converting certain digital signal. Okay. Now say when there is a signal, say it is saying that there is a high value, say let me call it 1 as high and 0 as low. Okay. It is saying that it is 1. Okay, means the signal is high. Alright. However, consider the situation that when it is trying to detect this signal as high, at the same time or within that conversion time the signal becomes low. Okay. Then what it will see is only low. It will not see any high that time, and then this will be an error and it will show the low value, or say low, and maybe next signal may be high, or maybe continuous signal conversion is happening. Okay. So at the time when ADC has started converging, at the same time if the signal has changed, because it is continuously changing, okay, and by any chance if it has become from high to low, okay, you will have the wrong conversion. And once I have given you this example 0 1 1 0 1, and say if you read one bit wrong, okay, your whole sequence of signal is wrong. Okay. So you may misinterpret whatever result you are having or whatever discretization you have done. Okay. Therefore, the sample and hold circuit stores the voltage long enough for the ADC to complete the conversion. Till this conversion from analog to digital has happened, the sample and hold circuit will hold that particular voltage input. Okay. Now this is about the sampling. Okay. The second stage of the ADC is the quantization. Okay. Quantization converts the sampled amplitude into discrete levels. So you have already the sampling done, now it has to be discretized. Okay. Now consider that the ADC has n bits, and if you have n bit ADC, number of quantization level required will be 2 to the power n. Say for example, if you have say 3 bit ADC, okay, the number of quantization level required will be 2 to the power 3 or 8. Okay. Now whenever you have quantization, there will be certainly error associated with it, because whenever you are doing quantization there will be certain approximation done, and this is exactly the reason of error. Okay. And the error will be equal to the actual value minus the quantized value. Okay. So whenever you are doing this second stage or quantization, there will be certainly a error, and this is known as the quantization error. Okay. Third stage is encoding. Okay, and encoding is very important stage, because this will decide your binary signal. Okay. So encoder converts the quantized level into the binary digital code. Okay. So digital output will be equal to binary code representing the quantized level. Okay. Say suppose an ADC has 3 bits, we have seen that number of quantization levels will be 2 to the power 3 or it will be 8. Okay. Now the encoder will do exactly the thing that is shown over this slide. Okay. Say you have analog range, say from 0 to 0.5 volt. Okay. Let me call it a level 0 of quantized level, and encoder will code it to say 000 because it is a 3 bit ADC. Okay. Now the next analog range of say 0.5 to 1 volt may be called as quantized level 1, and this will be coded as 001. Okay. Now say next stage of encode or next stage of analog range is say 1 to 1.5 volt. Let me call it level 2, and level 2 quantized level has been given a binary code of 010. Okay. And this is the exact job of the encoder. Okay. Now similarly the next analog range will be 1.5 to 2 volt, and it is at level 3 and the code is 011. Okay. Similarly 2 to 2.5 volt is level 4 and the binary code is 100. 2.5 to 3 volt, let me call it level 5 and let's code it as 101. Okay. Now this is the ascending order. Okay. 3 to 3.5 volt, it is level 6 and coded as 110, and 3.5 to 4 volt is level 7 and coded as 111. So you have all together 1, 2, 3, 4, 5, 6, 7, 8, okay, 8 quantization levels, level 0 to level 7 coded as 0012 to 111 for the analog range of 0 to 4 volt. Okay, and this is how exactly any analog to digital converter that we will see in a while does. Okay. Now say if the input voltage is 2.2 volt, okay. Now if you see this chart, 2.2 volt is somewhere here, okay, in the 2 to 2.5 volt level, and 2.2 volt will be quantized under level 4 and will be given a binary code of 100. Okay. So the digital output at this place will be 100. Okay. There are 4 most popular methods for conversion of analog to digital signal. We have a potentiometric AD converters which works on successive approximation methodology, and we have voltage to time conversion method, sometime also known as ramp type analog to digital converter. We have voltage to frequency conversion methods, also known as integration type, and then we have a dual slope integration method for analog to digital conversion. Please note that this is not the complete list, and we have several other types of ADCs, like we have flash ADCs, we have counter type ADCs, we also have a tracking ADC. A sigma delta ADC is very popular ADC in the current market. We have a pipeline ADC, and there are some more kind of ADCs available, but for our purpose these 4 different ADCs will serve the purpose. So in this course we are going to discuss this 4 methods of conversion of analog signal to digital signal. In the series, let us start with the potentiometric AD converter, which is based on a successive approximation method. Okay. The potentiometric AD converters is most widely used in general practice because of its high resolution as well as because of its high speed. The potentiometric type AD converters work on the principle of successive approximation. We will try to understand what is successive approximation right now. Okay. You can understand the successive approximation method like a binary search algorithm. Okay. So the successive approximation method works very similar to the binary search algorithm. Okay. The process is as follows. The ADC tries different digital values sequentially, and this starts with most significant bit or MSB and moves towards the least significant bit or LSB. Now this try by ADC is done until the output from a decayed assembly counter, let me call it a DAC, matches the input analog voltage. Okay. Once this voltage matches with the input analog voltage, this try will be stopped by the ADC. Okay. At every step in this try, the system generates a trial voltage. A comparator compares the input voltage with the trial voltage. Now the successive approximation logic decides whether to keep this bit or clear that bit. Okay. Therefore, the system approximates the input voltage step by step. Okay, and that is why the name is successive approximation method. Okay. A typical successive approximation based potentiometric AD converters looks something like this. Now this region, if you see, it resembles to a potentiometer, and that is why its name is potentiometric AD converter. Okay. Now here I have a voltage comparator, a programmed switch and a counter. Okay. Output of this counter is a digital output. Okay. Now if you see, this potentiometer is let's call it, or it looks like a voltage divider. We know that potentiometers works on a voltage divider. Okay, so it has a voltage divider network that has a coarse and fine steps. So you can actually set coarse and fine steps depending on the number of digits or binary digits that you require. Okay. Now the voltage divider network is connected to a voltage comparator through switches. Okay. So you can see that this is fed into the voltage comparator. Okay. And you have programmable switches over here. Okay. The voltage divider network is connected to a voltage comparator through switches. Now this compares the input voltage, let me call it internal voltage also, provided by a reference source with a unknown voltage. Okay. Let me call it V in as internal voltage and V reference as reference voltage. Now the comparator compares the internal voltage or the input voltage with the reference voltage, and if V reference is less than V in, we have seen that the counter continues counting. Okay. We have just seen that this is done until output of the DAC matches the input analog voltage. Okay. Now this V reference is less than V in. At that particular moment, this counting continues. Now at the point when this V reference is equal to input voltage, okay, at this particular point the counter stops and there is no further counting. Okay. Now the output of the comparator, which is of course an error signal, is fed into the logic circuit. Okay. Now this logic circuit operates switches to control the steps of the voltage divider network. So it's kind of feedback network that you can understand. Okay. The measurement sequence usually selects the largest step of the internal voltage first, and the magnitude of the steps decreases until the null point is achieved. Okay. Now the digital output is read on the counter that we have just seen. Okay. Now this potentiometric AD converters, if you see, have very simple principle of working, but they have very high accuracy, and this is one of the advantage of this potentiometric AD converter based on successive approximation method. Okay. It has a counter, if you see, okay, output of the counter is a digital output, means that you have a direct digital readout. Okay. You do not need any further interface circuit to have digital output. This is giving you a direct digital output, and therefore this is very good for precision measurement instruments. Okay. However, since it is using a bulky potentiometric type of system, the conversion speed is slow. Okay. You are comparing the input voltage with reference voltage continuously, means that you should have a stable reference voltage. Okay. So this is one of the important requirements of this potentiometric AD converter, and you can say that this is also a kind of disadvantage, because getting a stable reference voltage source is one of the challenge, or it's little challenging. Okay. These are not suitable for high speed applications, and we have seen that although it has very high accuracy, it has very good precision also, but then also it is more preferable for low speed applications or low speed operations. Okay. We have several applications of this potentiometric AD converters based on successive approximation methods around us. Like for example, it has very good application in digital voltmeters or DVM. Okay. As I have earlier also mentioned that they are favorable for precision measurement instruments. Okay. They are also useful in calibration systems, and most of the laboratory measurement equipment possess this potentiometric AD converters. Okay. We have another kind of AD converter that is very important for us, which is voltage to time AD converter, sometimes also known as ramp type AD converters. Okay. The voltage to time conversion ADC, commonly called as ramp type ADC, is also called single slope ADC. I have earlier mentioned that we will also study a dual slope integration kind of ADC, but this voltage to time AD converters are also known as single slope ADC. Okay. As the name suggests, you have a voltage to time AD converter, means that this AD converter converts voltage to time or voltage to time interval and then converts that particular time interval into digital number using a clock and a counter. A clock and a counter is required because what you are doing is you are measuring the time interval, say depending on the voltage, say if it is less or it is more, okay, say x and say x plus say 10x, okay, I will convert it to time interval, maybe say t or and say t plus another 10t, okay. So you have small time period or time interval, you have larger time period, okay, or time interval, okay. Depending on this you can digitize, say maybe let me call this low and let me call this a high, okay. By this also you can do analog to digital conversion. So this voltage to time AD converters works on converting the analog voltage into a time interval and then converting that time interval into a digital number using a clock and a counter, okay. In the voltage to time ADC conversion, the magnitude of the input voltage is converted into the time interval and then to the digital count as I have mentioned. So idea is very simple. Idea is to have higher input voltage converted into longer time interval, and once this conversion for voltage to time is done, the time interval is measured by counting clock pulses, and that is why I have initially mentioned that you need a clock and counter to measure this digital output, okay. So once this conversion for voltage to time is done, the time interval is measured by counting clock pulses. This voltage to time AD converter has digital counter to measure the time required for a voltage ramp to rise from 0 to input voltage level, okay. Now the time for the ramp to drop down from the input voltage level to 0 can also be measured depending on how you are using or what kind of slope you are using, okay. Now this converter may be used when the ramp is either positive going or negative going. What I mean to say that, say I have a ramp signal, okay. Now say it has a positive slope, I may also have this negative slope, okay. In that case, say maybe this is a signal for example, okay. So what I am telling that the digital counter is measuring time required for a voltage ramp to rise say from 0, okay, to say this is say input voltage, all right. Say this is what it is measuring. What I am telling that the time for the ramp to drop down from this input voltage level to say 0, this can also be measured, okay, depending on what kind of slope you are preferring, okay. So these converters may be used when the ramp is either positive or either negative, okay. Now this is a typical voltage to time AD converter. You can see that I have a ramp generator and output from it is going into two different comparator. I am calling this ground comparator, or sometime I am also calling say first comparator, okay. Output from this ramp generator is also fed into this input comparator. Let me call it also a second comparator, okay. Then I have oscillator, main gates, counter and so on, okay, and this is the input voltage supplied to the input comparator and the ground comparator, okay. Internally generated ramp voltage is fed to two voltage comparators as you can see over here, okay. Now ramp generators can be of different type, although it is beyond the scope of this course, but then also one should know that we can have different ramp generators. We can have a constant current ramp generators, we can also have a Miller ramp generator, we also have a bootstrap ramp generators and so on. But the idea is the output voltage, or the we call it ramp voltage, is directly proportional to the time, okay, because if you remember our aim is to convert a voltage signal into time interval, okay. So say VR, or the ramp voltage, is directly proportional to T, or if I am removing this proportionality, I am putting one constant S. Let me call it a ramp slope, okay, and let me call this equation 1, okay. So regardless of the ramp type, I have ramp voltage VR equal to S into T, where S is the ramp slope and T is the time interval. Okay. The ramp voltage may have either a negative or positive going slope, as we have just now discussed. Okay. Now for our discussion, let's consider that a ramp voltage with positive going slope is available. Okay. When the input voltage is equal to the ground voltage, the ground comparator emits a start signal to a gate. Okay. I am talking about this particular gate. Okay. So when the input voltage is equal to the ground voltage, the comparator or the ground comparator or the first comparator emits a start signal to a gate which opens and permits the passage of pulses of a clock from a crystal oscillator to a digital counter. Okay. Now when the ramp voltage is equal to the level of input voltage of the second comparator or our input comparator, it produces a signal to close the gate, therefore further counting is prevented. Okay. Say ramp generator generates a ramp voltage VR equal to ST that we have seen in equation 1. Okay. At the comparison point, V in is equal to reference voltage VR, which is equal to ST. Let me call it the second equation. Okay. Now from this equation, it is very clear that the time interval is equal to the input voltage divided by the slope. Okay. Let me call this third equation. Okay. Now the counter counts the number of pulse during the converger time. Okay. And the digital output is equal to clock frequency into the measured time interval. Okay. Let me call this digital output as N. This is equal to the clock frequency into the measured time interval. Okay. Now putting the value of T from equation 3. So T we have already seen is equal to V in by S, and if I put das V in by S here in equation 4, I have digital output N equal to F clock into V in by S. From this equation, it is very clear that the digital output N is directly proportional to the input voltage, and we can say that the digital count is proportional to the input voltage, and ultimate aim of this analog to digital converter was doing this. So now I have a digital output which is proportional to whatever analog signal I am feeding at the input. Okay. Now this voltage to time AD converters or the ramp type voltage to AD converters have several advantages, like it has a simple circuit architecture and have a low hardware complexity. Okay. You have only two comparators and a ramp generator, and of course you have counter and other things to have digital output, but then also the complexity is very less. Okay. This voltage to time AD converters have good linearity between input voltage and output count, and it also has a moderate resolution capability. Okay. Digital interfacing of this voltage to time AD converters are easy with counters and processors. Okay. They have minimal component requirement, as I have earlier mentioned, and they are suitable for low speed measurement systems. Okay. Because the conversion speed is slow, and that is itself is one of the disadvantage of this AD converter. Okay. They are also sensitive to noise and signal fluctuation and require a highly linear ramp generator, which is sometimes impossible to get. Okay. So they have limited resolution for high speed application, and that's why I have mentioned that they are mostly suitable for slow conversion kind of applications. Okay. And they are not suitable for high frequency signals. They are susceptible to clock instability errors because the digital output directly depends on the clock frequency. Okay. The comparator offset can introduce measurement error, and it should be avoided by choosing appropriate comparator. Okay. Poor performance in high speed data acquisition system is another disadvantage of using a voltage to time AD converters, and therefore we have other kind of AD converters also available, and we will discuss the other two important AD converters in our next class. Thank you.